If you're just joining us, we'll get started in just a few minutes. Welcome all, and thanks for your support of BAMA by your attendance. This is our first ever virtual meeting, and we're giving it a try. Well, welcome. I'd like to take this opportunity to just, thank you all for being here under these strange circumstances. I hope that by providing you a virtual talk, we're providing you something that, helps with your life. And I think that our speaker tonight, his topic is exactly calculated to do that. First, before introducing Professor Harriss, I want to mention our next talk. It's going to be December 1st, Tuesday night, also on Zoom. The speaker is Steve Prettle of Stanford University, speaking about life in curved spaces. This grew out of a project using virtual reality to see what it would be like to move around in strange strange non-Euclidean spaces. So I hope you'll join us on December 1st for that. I want to be brief in my introduction to Professor Edmund Harriss of the University of Arkansas. He's a dynamic speaker. He is a wonderful mathematical artist, and I'm proud to call him friend since we were both residents at the semester program Illustrating Mathematics at the Institute for Computational and Experimental Research in Mathematics a year ago. Without further ado, I will turn it over to Professor Harriss.
Hello, and welcome to everyone. Thank you for coming. And I'm going to handle the first tech piece of switching over, and hopefully this will work nicely. And there was already some debate in the chat as to what this is, the answer to that, if you saw the chat, is it does depend a little bit on exactly what you mean by the word tiling. So if we really want to get into definitions, but this are some Penrose tiles. These two shapes fit together, and you can make an infinite tiling of the plane with them. In fact, in lots of different ways, but the key thing here is not really the tiles, it's the two hands for me. So I did my PhD on the Penrose tiling and generalizations of it, and started during my PhD to do work on making mathematical graphics and mathematical images, and felt the power they had to share mathematics with people. But you could only see mathematics in an image. When you gave people these tiles, they could do mathematics. They could put their hands on them and they could interact in different ways. And so this got me onto the sort of long quest to really think about how can we bring mathematical ideas into physical reality in different ways. And this talk is going to be about the making of objects that have that property of showing the mathematics, but actually the machines that make the objects are themselves interactive sort of reifications of mathematical ideas. But following my thesis and that insight that handing people these two tiles, I didn't need to tell them anything. They could just start putting them together. I sort of had this quest to create other systems that people could play with naturally and explore mathematical ideas. And so this is a system I designed called Curvahedra, which has these individual pieces that hook together, and you can explore all sorts of mathematical shapes and notions of curvature through them. And I will stop sharing briefly, and I suggest you get the camera bigger. Hopefully this will work. So here is that model you were seeing being made. And it's a lot of fun when you drop it on the floor. The camera angle isn't perfect there, but hopefully you get the idea. But with this, I can go into sort of math exhibits and so on, and shock parents by telling the kids to pull the math art off the table and see what happens, and set a very bad example for all the other tables. But again, it's this aspect of being able to put your hands on, interact, create with mathematics. And this is something that we don't often get to see or do unless we're professional mathematicians. And then we have to interact with the mathematics through the esoteric symbolism of mathematical symbols. So now I've promptly lost. I have far too many windows open. I will remind myself next time I give a talk, I need to reduce the number of windows so I can more easily
Edmund, as a
find.
distraction, I could do that poll that you asked me to set up.
Yes, that's a good idea.
Okay, everybody, here's a poll. Thank you for answering our poll.
And
We've got 40 out of 53 answering. Come on, let's turn out the vote. I suppose some people might be on devices that don't permit them to respond to a poll. But it seems like 60% of the people say they have never heard of CNC and CAM, and 30% have heard of it, 8% have used it, and 1 uses it regularly or professionally. So we have quite a mix of expertise with this kind of concept. I wanted to
hopefully,
go ahead.
So hopefully this talk will give interesting things to all those different levels. I was curious as to how people had interacted before. And I will definitely, for those of you who've never heard of these things, give a discussion. And hopefully by the end of this, everyone who was in that, gave that first answer, will have moved up to the second level, have at least heard of CNC. And next time you get asked, we'll remember that. So let me go back to my desktop and close the poll. Okay, so here you can see lots of people interacting with this system. And as I was exploring these options from making these objects, making objects you could put into people's hands, it naturally, if you wanted to produce things at scale, I can't individually hand make all the pieces that go into a system like this. So looking at some of the automated technologies that allow you to create was something that came naturally. And these are made on a laser cutter, which was a very nice two-dimensional machine. And so I could get very direct control. I drew a path in something like Adobe Illustrator, and the machine would then go over that path with a laser, and for good or bad, whatever I had drawn would be cut out of the material that I was attaching it to. Whether that be, and you can see here, these are Mylar, but here is the same system made larger in wood. And here is a closer image of the sort of objects that you can make with this system. This is the classic ball. This was the first thing I made with this system was just this icosahedral ball. And I looked at it and thought, wow, I think this is something I need to push further. So once I started exploring what you could do with cutting things out of two-dimensional sheets, I of course wanted to go larger. And that's where you move from a laser cutter to something, this is made on a 3-axis CNC. on the island of Heimaey, which my wife is from in Iceland. And this reference is getting more and more dated. But if you remember in 2011, there was a big volcano in Iceland that stopped flights across the Atlantic called Eyjafjallajökull. And this is it erupting. No one has been able to prove whether or not the sculpture had any role in the volcano erupting. But this is, again, working with that idea of how do you interact with mathematics? How do you play with ideas of mathematics? And then you make objects that, in this case, the way this shape was not something I designed. The people who came together to do the final build used polydron pieces to make a small version of this object. And then we voted on which of those we were actually going to build. So that's a sort of, there's a lot of nice mathematical ideas of sort of spaces of shapes and questions of how many different shapes can you make with 20 equilateral triangles? And so this, again, the mathematics comes in that sense from the exploration after the making. And so in a similar light, this is a piece in a walnut grove, and again, nice cut shapes from two-dimensional pieces. So hopefully for those of you, sorry, that's too loud, but so that was a little bit of video of a 3-axis CNC machine. And so as you can see, it's a spinning router. And now I'm going to try and do things with my hands. So you have this router spinning, and that router is on a gantry that can move up or down. You saw it in that video, the bit being moved up and down. That piece that goes up and down is then on a further thing that can move left and right. And then that whole system moving left and right is itself on a gantry that can move forward and back. And so I can put 3 numbers in, which give me the positions of the height, the X position, and the Y position of the machine. And that controls the tip of the router. And then what I'm doing on top of that is giving not just one position, but a whole list of positions. And so you move around following those positions. And as you move around, you can carve different paths with the machine. And the pieces you've seen so far are relatively straightforward. They are, you draw some 2-dimensional shape, and you're only really using the height to cut away material, go deeper, cut away more material, go deeper, cut away more material. You're not doing anything more sophisticated than that with the height. And the problem when I wanted to go beyond that to deal with 3-dimensional systems was that it was not easy in the standard tools you use to control CNC machines to just do an arbitrary path, to just make all sorts of 3-dimensional curves and tell the machine to carve along that. The software was always set up for you to give it the object you wanted to have coming out, and then it would create the paths that would generate that object. And that wasn't what I wanted at all. I wanted to be able to draw the paths and have the machine carve them. And so mathematicians are very bad when they see a problem like that, because their reaction is often, well, how hard can it be? I can understand all the fundamental pieces. I need to do this. So let's have a go. And I did that. And the result was this software, Camel. It's a plug-in to another piece of software called Rhino and Grasshopper that you might or might not have come across. But that allowed me to make a piece like this bowl that was this was the present from the math department here in Arkansas to Chaim Goodman Strauss when he stepped down as chair. And the way this bowl was made, this surface that you see in the top of the bowl never existed before it was made by the machine. I just drew these curves that the machine would make. And here are those curves. These are the curves that I drew. And then I just put these curves into the machine and told it move along each of these curves. Now, one thing that's interesting there's actually an interesting difference between the surface you get by connecting the curves here and the surface that you actually see in this bowl. And you can sort of see that the surface moves in and out. There's a sort of corrugation to the surface in the actual bowl that's not present in the lines as they're drawn. That comes from the fact that you're not moving an infinitely thin bit through the wood. This is made with a 5/8 of an inch ball end mill. So you're moving a sphere with hemisphere with a 5/8 inch diameter through the wood. And so as the center of that, the central bottom of that sphere moves under the path that we describe, the wood that's removed varies depending on how the different levels of cutting relate to each other. And so you get this intricate, detailed structure that's actually made pretty quickly on the machine because there are not a huge number of paths here. So you get this intricate structure, this sort of beautiful design. Well, I guess I made it, so I'm biased, but you get that comes from the interaction of the path you drew on one hand with the behavior of the machine. But on the computer never knew that was what it was doing. I had a sense of what it was going to do, but this was still quite early in my exploration. So I knew it was going to do something good. I didn't know exactly what was going to happen. And it was very pleasing that it worked out quite so nicely. And here are a couple more views of what those lines look like.
Edmund, if I could interrupt with a question.
Yeah.
Do you experiment with a less expensive material, or did you go straight for the wood with that one?
We did some cutting in foam, but generally, I mean, wood is not that expensive a material. The cost of the block that came from this was about $60, and the whole cost of this process was $60. So I felt like if I messed up, as I was not charging, the math department could put some of the fee for me that it was not paying into getting another block of wood. So these curves here you're seeing, this is the design for the base of the bowl. And one of the things that was very pleasing for me about this bowl, because I wrote the software that converted these paths into the actual paths that the machine would cut, and I drew all these paths. I feel like this is a handmade project in an odd way. So it's handmade in mathematics, if you like, because every single movement that the machine made came in some way from lines of code that I'd written. So let's have a look at the mathematics that starts to emerge when you play with these ideas. And so this is a simpler example. This wavy surface comes from the equation at the top. You give different, every time you fix a value of y, that gives you a particular curve, and as you vary x, and so you can see the different curves that you end up drawing. And we're going to think about carving each of these curves. So this is those curves and the surface, that a rough idea of the surface that we're going to make. And here is a couple more views of the curves. And now this is what the software comes up with. So one thing that you need to think about when pushing a bit into wood, and you saw that in the first video, is that you can't just push the largest bit, you can't just push it deep into the wood and start moving horizontally. That's going to cause a lot of problems. The forces involved are, quite high. So what you need to do if you're cutting down is, instead of just going along your path, you need to create a set of levels that you cut out first. So when you come to make your final cut, you're not removing that much material. And so this is the set of all the paths that the machine will take in order to create that surface that you saw. And here is the resulting piece of wood. So you can sort of get a sense of the three-dimensional nature of it. So in both these cases, I am deliberately ignoring the fact that the machine that I'm cutting with isn't going to cut along the path that I'm drawing. It's going to be moving along that path, but the place where the place that's moving along is not the place where it's necessarily interacting with the wood. It's the base of the tool. And so here you can see a diagram where you're starting to get into some mathematics to avoid that problem. So think about, let's zoom in. I apologize for the pixelization of these images. I need to make some which are of a higher quality, but you still will get the basic idea. So these horizontal lines, those are the rough cuts where you're just removing material. And they finish off in this curve here. And that sort of finishes the roughing. That's the process you do to remove the material that's just in the way, just need to get rid of. And then you want to do the finishing to get a good quality. And the red curve is the curve that we want to cut. The orange curve is the curve that we're actually going to move the center of the tool along. And so you can see when we're trying to cut horizontally, the center of the tool is going along the path that we wish to cut. But when we start to move at an angle, because the tool, the bottom of it is a piece of a ball, which in this case you can think of as being a circle. If the center is moving along this orange line, the place where the tool is interacting with the wood is going to always be along the red line. And I'm teaching Cal 3 at the moment, that multivariate calculus. And there's just so many bits of that that turn up in doing CNC. And so if you remember from doing a course like that, ideas like the tangent to the curve and the normal, I need to use the normal to my curve to offset the center of the ball, and then I come down from the center of the ball to the base of the ball to move my tool. And I want to do it from the base of the ball because that's something I can measure accurately into the material. If I do it, if I control the center of the ball, that's some distance above the base. It's nicer to just think about controlling the base. And so I can then zero the machine. That's when I set up the origin of my axis. So the position that I'm going to consider for those three things that I have moving to be 0. I can move that until the tip of the tool touches the top of the surface. And the way that I generally set things up is to set that as the 0 height. So the top of my material is the 0 height. When I'm cutting, I'm always cutting in negative values. If I'm in positive values, I know I'm safe to move around. I'm not going to interact with the material. So once you get to control paths with the concept, well, control a machine with the concept of a path, you can sort of ask what interesting mathematical paths are there out there? What paths can we control? And you might recognize that this is a space-filling curve. And space-filling curves have a problem. They're very hard to visualize. When someone claims something as a space-filling curve, generally they're showing you an approximation of a space-filling curve. Because if you actually see, the clue is in the name, a space-filling curve fills space. If you see the actual object, it just looks like a fully black region. The curve gets everywhere, it fills space. So you have to see it, you actually look at an approximation, these curves that wind around. But if we put that object into 3 dimensions, as we move along the curve, we can also change the height. And that path becomes this piece. And we can actually, oh, I think I failed to put in the video of this being cut. My apologies. I can, however, give you a sense of this is that object. And it's worth looking at from this direction because you can see all these different plateaus. And so now I'm still carving an approximation of a space-filling curve. But as I've added this height, as I move along it, what that actually gives me is a nice limiting process. If I doubled the resolution of the curve that I was making, it would spend more time wandering around in a particular region, but the height drop from the start to the end of that region would be the same as it is in this case. And so as I increase the resolution, the surface wouldn't change dramatically from this. And so this is an approximation of an object which I can consider a limit out to infinity. So I can consider this to be a view of a space-filling curve that's sort of shows more than just that approximate image. Because if I went to that limit, I filled space because of the height, I would still get something that looks roughly like this. These this sharp line where you've got the plateau would still exist. part of me wants to really make a driving game where you're in a car and you have to drive around this curve, which would be tricky because there's so many bends. And then you get to places where you could sort of fall back to earlier. You'd start at the bottom, and to begin with, you would hit walls, so it would help you move along. But as you get close to the top, you could fall. If you drove off, you would fall quite far. And I would love to see the different the scenery that you would get from looking at this in virtual reality or something like that. And controlling these machines is also, I found, a very useful teaching tool. And so these are all examples of student work. And we ran a one semester class with students from across it was an interdisciplinary class. We had history majors, social science majors, social work majors, alongside mathematicians, computer scientists, and chemists. One thing I discovered very quickly in that course is that the math majors knew a lot more mathematics that they couldn't use. When you ask people to actually start dealing with the sort of simple mathematical problems that come up when you're trying to draw some paths to do something interesting in a piece of wood, the math majors could, they could easily solve differential equations, but they couldn't actually write a differential equation even when that was going to solve the problem that they were having. And so I think one of the strengths of this course, it was actually as an applied practical use of mathematics. And the students from it, that was one of their consistent comments. They felt that following the exercise in art of making some pretty but clearly useless pieces of wood, decorative, certainly, they actually understood a lot more about how mathematics works and how you use mathematics to do something. So I think this is, well, the other aspect, it was a course which I didn't have to talk about grades, because through the course they had 4 or 5 chances to carve something. And the first exercise was literally draw a path, cut it in wood. And some students finished that assignment to the letter. They drew a path and it was cut in wood. It was not very good. And those students in the second one made some of the best things, because when they saw what other students had done with that assignment, they realized they'd just blown one of the 4 chances they would get to do something interesting. So it's a nice, from a pedagogy point of view, having this limited resource, so you have creativity, but their creativity is focused into these 4 acts of making through the semester. That meant they could let their imaginations run wild, but they had to come in and focus to do a specific design in the final, at the final point. So I actually told a lie earlier in this. So this was actually the machine that I saw first when thinking about CNC. All that nice 2-dimensional stuff came after I'd started writing software to control this. So this is a 5-axis machine. As well as being able to control the height, the 3 dimensions of space, you can also control the angle that this tool runs at. And you can see that the tool is changing its angle as it moves through the wood to make this surface. And the problem here was this was a very bespoke machine that somebody had made. And so it didn't have any software which could write paths for it. And so I didn't start with the 3-dimensional control problem. I started with the 5-dimensional control problem. This was about 2 months after that, and I had the machine carving a massive tree stump into a surface. So I was able to get some good solid early progress. But 5-axis opens up so much more mathematical opportunity. And so let's look at this. So this is now a smaller and more delicate machine called a Pocket NC, which is a lovely little training machine, because if something went wrong with that big machine that we were just looking at, that would have been quite fearsome, quite scary. Whereas this machine, and you see it makes this delightful singing as it goes. This machine, you just break the bit. It's very hard to do any serious damage. But what we're doing here is actually, we're carving this surface, it's called a pseudosphere, and we're carving it with paths that are really designed for the geometry of the surface. And so you can see that the step over, the distance from one of these paths it's cutting to the next one is actually pretty big. So at the base, it is stepping over 3/4 of the width of the tool. And so the overlap between one path being cut and the next is quite small. So let me show you the piece that was being carved. And this is a challenge for the camera, but maybe you can see that sort of starting, it's sort of starting really quite far apart, and yet the surface is really quite smooth. And we're carving, the paths we're carving are the ones you can see carved in more detail here, and they're called the asymptotic curves on this surface. For anyone with a little bit of differential geometry, these are the curves that are always along the ruling direction for a negative curved, for the negatively curved pieces of the surface. If that didn't mean anything, don't worry. The key is to look at this object and see what it's doing, and to understand that because we can control these curves and understand how these curves, we get a good way to carve into the material. And we get that from thinking about that question of controlling the machine, not the output object. In fact, we can think about new ways to investigate how a surface can be carved. And this surface, which is called the pseudosphere, that is, has these particularly nice asymptotic lines that are pretty easy to run. Now, can I just check that I'm sharing my, you can now see the CNC machine again?
Yes.
Good. So this is another object that we can use, this idea of being able to go from idea through path to machine carving. So this is a surface called the Bath sextic. It's the solution to a degree 6 polynomial in X, Y, and Z. And it's, in order to make it, what we did was actually, and this is joint work with Silviana Amethyst at the ISEM semester that Frank mentioned. So we took that mathematical surface, which is a bunch of equations, Those equations give you the surface, they don't give you the paths. But from those equations, you can get a point, any point on that surface, and you can draw curves on that surface. And then at each of those points, you can work out what the normal direction to the surface is. In other words, what direction do I want to have my flat-ended tool so it carves that piece of the surface really nicely? And so here you have the machine moving along those curves. And it's worth stating, so the curve that this machine is following here, we didn't create a three-dimensional model of the surface and then ask the machine to carve that surface. We created these paths on the mathematical surface and then asked the machine to move along those paths. And you can see, if I play this again, as the machine moves, it is always staying so that the tool is at right angles to the surface at the point that it is cutting. And as I said, those pieces come pretty directly from the mathematics of this surface. So that sort of concludes the main discussion. I thought I would finish though with some explorations of other things you can do with interesting CNC tools. And so here, for example, is stepping up from making little mylar pieces to making things in metal. And this is made on a tool called a plasma cutter, which I like to think of it as harnessing the surface of the sun to cut pretty metal, because it uses electricity to create a plasma, which is similar to what happens on the surface of the sun. And that plasma cuts straight through ferrous metals like this steel. The other thing that's nice about this ball is you can see this looks pretty spherical. And if you've done any sheet metal work, you know that bending sheet metal so you get nice smooth curves is a classic challenge. Well, so this was, I made this bending by hand with no machines and no particular skill. And yet the curves are, I would say, you know, they're pretty nice. I'm very, very proud of how spherical this came out. I have to admit, this is the second one I made, and the second one I made involved a lot of swearing and fighting and clamps. But the second one, I really lent into the mathematical structure. And again, mathematics that for people who are familiar with it, if you go round a loop on a surface, the amount you turn as you go around that loop is related to the total curvature inside that piece of the surface. There's a beautiful theorem called the Gauss-Bonnet theorem. And I used the Gauss-Bonnet theorem directly to make this ball. The nice curves come from the fact I was not trying to bend the steel. I laid out the triangle flat, and then as if I was staying on the same surface, pulled the two ends of the triangle together and staying in the surface. So the forces that I was applying were always parallel to the metal. And the Gauss-Bonnet theorem was then what introduced the curvature and did a very nice job of distributing that bending force. And so the metal got bent smoothly over its length. If you just take a piece of steel and start to bend it, as soon as it starts to bend in any place, that place will make it easier to bend there. And so you won't get a smooth curve. You'll get a piece that comes to a curve and that again comes back. And here is the powder coated version of that, which now sits in our honors college. And this photo is from Andy Shoup of the Arkansas Democrat Gazette. Now, plasma cutting is very cool and can do stuff with metal, but if you really want to get serious on these technologies, water jet cutting is hard to beat because it puts a high pressure jet of water with little bits of garnet or diamond in it. And that can cut through just about anything, which is a slight problem when you want to actually provide support for the things you're cutting. And if you see here, these metal slats have been chopped up. And this is not just a water jet cutter, this is a 5-axis water jet. And so you can change the angle of your jet. And so here you can see the head of it, and it has these 2 rotational axes. And so it can change the angle at which you're cutting. And here we're cutting through a block of wood, and you can make these beautiful curved hyperboloid cuts. And you're able to see in this some of the details of the directions it was cutting as it went through. And so the geometry that starts to come in here, because you're no longer controlling your tool as a point, your tool is now a line of water. And so you can cut things like ruled surfaces. And because you can cut anything, why not cut a brick? And so this is a brick which has had a surface cut out of it. And here is the surface that got cut. And it's quite magical. It's the magic of being able to cut ruled surfaces, that you can use this straight line tool to cut a curve which seems to bend back on itself. And so if that doesn't show the power of geometry and thinking about controlling that, I am at a loss for what will convince you. And so here are some nice photos of that brick from 3 different angles. So I wanted to finish with a failure. And so this is and it's sped up. This is an experiment with doing 3D printing in clay using these sorts of ideas where we draw the path. And we decided to make the tool, instead of go around in nice smooth curves, go up and down. And this proved problematic. As you can see, right now, it seems to be working quite nicely. And it works nicely for a time. The problem we had is that we couldn't get it to consistently raise up. We're trying to clean it there, but it's actually going wrong now. And what's going on is that the material, that the head is moving too fast up. And because you're controlling the path, you're not reacting to where the material is. And so instead of landing nicely on the clay that we put down before, we get this rather beautiful mess. And so, of course, in doing this sort of experimentation, you can get some really nice results some of the time, but you also spend a lot of time dealing with things that just don't work. So that finishes my talk, but I would like to give a pitch for this project that I am part of, which is called Mathamalchemy. It's led by Ingrid Debussy, who is a mathematician at Duke, and Dominic Edmund, who is a Canadian artist, fiber artist. And this is one of the first things we've made. And you might notice this is some of my my CNC work in there. Some of the objects that I've discussed today are present in these photos. But it's this massive, this is one piece of a massive mathematical wonderland that you should watch out for, because hopefully at some point after we can actually get together in person and finish and bring it all together, assuming those times will come eventually, this will be doing a tour of the country, and it's this lovely mathematical, whimsical mathematical wonderland. So thank you so much.
Thunderous applause, thunderous applause. Thank you, Edmund. I'm delighted. We do have time for questions, and we could try chatting them. I can also empower people to unmute themselves. Let's try that. Yes, you now have the power to unmute yourselves if you wish.
I have two questions, Mr. Harris.
Yes?
So could you explain the Gauss-Bonnet theorem again? I didn't really get what that was.
Short answer, no. I think I said at the beginning of that, for people who understand what that is, it would be something that was familiar. It's to do with, as you go around a curve on a surface, you can ask how much you turn. And so when you do a full loop, you can study how much you've turned in making that whole loop. And then that tells you something about how much the surface that you just cut off with your loop is curved. I have a paper that's an explanation of that for a general audience. And so I probably, if you email through Frank, I can send that to you after. But a full explanation of it really requires a graduate level course in differential geometry.
You had another question?
My second question was, how much mathematics and computer science do you have to know to be able to like start making your own wood projects, sort of, I guess? Like how much you have to learn?
As much or as little as you already know. So I have some systems that I use with to teach artists to use CNC machines, and your generic art student does not have a strong mathematical background. I mean, basically you have to be able to draw a path. If you want to control the machine by drawing paths, you have to have some way of drawing a path. So you could hand draw a path and take a photograph of it and then use a system that can turn that into a vector path that the machine could then cut. Or you could use something like Adobe Illustrator to draw a path. So the amount of mathematics you need to have is whatever you know. I would say, though, that the more mathematics you know, the more opportunities and options can come up, and the more ways you can interact with the system to do more and different things. So,
like for example, maybe like trigonometry at least, to be able to do like curves and stuff.
Well, we have a sense of curves with no mathematics at all. And so anytime you can draw a curve with mathematics. So the trig or algebra 2 are where you're first looking at curves drawn with mathematics. So those would be places you could definitely start using those curves to directly make things. But I would say there's no level of mathematics that's required, and there's no level of mathematics that can't be made useful if you try hard enough. And trig would certainly be something that could be made useful.
Okay. Thank you.
Are there other questions? We'd be glad to hear from you.
I had a question. So what is your advice regarding the students who want to get into differential geometry? Could you recommend maybe like a book or a video or some kind of a resource?
So the book Experiencing Mathematics by Dinah Tamina and Derek Henderson. No, Frank will know. What is Henderson's first name?
David
Is
Henderson.
it David? Sorry?
David Henderson.
Yeah, and David Henderson. That is a beautiful example of lots of geometry done through sort of physical investigations. And so that's definitely the book. And even better, it's available now as a free ebook through the Euler project. So you can get the best thing available on the topic, spending zero.
Thank you.
Are there other questions?
Yeah, hi, Edmund. This is
Hi.
Tim Sylvester. Good to see you again. It's been a couple of years.
Hi.
Andrew and I are here. I was wondering, do you have experience using commercial CNC machines for hobbyists like the X-Carve or Shapeoko? I mean, these things are like around $2,000, which is, I mean, if somebody wants to get into this, that's close to being approachable. Do you have experience with those?
Yes, and they're mostly. I mean, they're pretty good, especially if you're not trying to do serious production on them. But from the hobby, so occasionally you'll get problems, or you'll need to do some fixing on them, or you're not going to run them at high speeds. But generally, you're not going to do a project where you have to make 1,000 pieces in a week. And so they are fantastic for hobbyist use, and they really open up all the possibilities. So yeah, I think they're pretty nice machines, and they're getting better.
Yeah.
What kind of time was involved in like making one of the pieces for the Barth sex stick on the small machine?
So this is the Barth sextic model. Each of these pieces takes, depending on how hard I push the machine, 3 to 6 hours. And there are 20 of them. So in order to make this, that's a significant investment in time. And because every time you carve one of them, it involves 3 different tools. And so it's not even something you can, and you also have to watch the machine in case something goes wrong. I was cutting this out of ash, which has very variable hardness. And so I had these problems of it suddenly shifting its position, because it was literally getting stuck in a small piece of the wood, and the rotary axis couldn't hold position. So you need to be watching the whole time. So that piece is a serious investment in time. I am hoping, I need to make at least one more, because as I said, Sylviana Amasis, I work with her, and she did a lot of the toolpath work, and I need to give her a copy of it. And then I'm hoping to make one more. And then I'm just going to make that for sale for $15,000, and I'll be happy if it never sells.
So how long did it take, like, overall to complete that?
Well, on and off, we were working on the initial design and the testing over about 3 months. And then the actual manufacturing time of this is, well, I mean, just the manufacturing time, so probably averaging out at 4 hours, so 80 hours of cutting.
We had a question in the chat about whether it's possible to hollow out the middle of wood. And I think that
you can do things like this. So if you can,
it's all based on a straight path going into the wood. So you can't curve around. And
because you can go in and change your angle through one hole. If you make one hole, you can then do a bunch of directions, and so you can carve out quite a lot through a small hole. I don't have good examples of that out with me, but you can do things like sort of make a ball within a cage, so the ball is loose, but the ball is larger than the cage, which is made from a single piece of wood. Tricks like that can be done on the 5-axis.
At some point, we'll stop the recording, but does anyone have a question that they'd like to get recorded for future listeners to this BAMA program? Well, then let's move. Wait, did I hear a question?
Where can we access the recordings after?
We have to figure out where the recording will be posted. There should be a link from the BAMA website. So just be sure you know how to find the BAMA website. And we'll get that information there presently. No, we don't have a plan yet, but it's going to happen. Well, this ends our formal proceedings. I'm going to stop the recording, but you're welcome to stay and visit. You can unmute yourselves and we'll see what happens. Thanks all for coming.